I'm the director of the Institute for Data Analytics at Acadia. And thanks very much for joining us this evening. Dr. Luis Torgo is our special guest who's going to be teaching you lots of great things about data science and using R tonight. And just let me tell you just a little bit about Dr. Torgo. He's the Canada Research Chair in Spatial Temporal Ocean Data Analytics at Dalhousie in the Faculty of Computer Science. He holds appointments also as an Associate Professor in the Department of Computer Science at the University of Porto, Portugal. And he's an invited professor at the New York University, actually, in the Stern Business School, where he teaches masters in science and business analytics as well. Lewis's favorite language is the one he's going to be telling you about today, R, and in fact has written a book, and it's in its second edition. I think he'll probably tell you a little about that. So if you like what you hear today, you can learn more through that book. His research interests are in the area, certainly of data science, with a strong focus on predictive analytics, particularly for data that involves both space and time. For example, I know that he's likely done some of the work with Dr. Matlin at Dalhousie and others in the area of ocean research and tracking of vessels, for example, and you know, perhaps even fish and things like this. And so that combination of both spatial information and time, and has recently been focusing on modeling rare events, anomaly detection applications, for example, in the area of fraud detection, predicting extreme values and monitoring activities for anticipating things that are out of the norm. So it's really a pleasure to have Dr. Torgo with us tonight, and I'm going to turn things over to him. Thank you very much for being here, Louis. Appreciate it.
Thank you, Danny, for the nice introduction, and you know, welcome everybody to this very short course on using R for data science. So I will start the way that I should not, which is by apologizing. So, and the reason why I'm starting by apologizing is because I know that I have too many material for the 3 hours that we have here. So I'm sure that I will fail miserably in trying to present you all the slides that I prepared for you. But I thought that, you know, well, I might as well leave you with the material, and then if I don't have time to explain, you know, in a nice way or a comprehensible way some parts, then you can contact me later on, but at least you have the materials, and you know, I think it's better than not having them. Okay, so that's, you know, kind of a warning that I may need to rush some parts, but you know, just feel free to contact me later on if some of these things were not clear. Okay, all right. So let's start from with a small overview of you know, the typical data science or data mining workflow of any project, just to give you a sense of perspective of what we are going to talk during these 3 hours. Okay, so typically here we have a series of major steps that normally one a data scientist needs to go through when addressing some particular problem. And it starts, of course, with a part which is mostly interfacing with you know, the data owners, and which obviously we are not going to talk about. Moreover, because it's something that frequently is more connected with soft skills than other things than data mining in itself. But it's indeed very important that we don't skip this and maintain a good, you know, communication channel with our end users. Okay. Then we typically need some data pre-processing stages before we can really start to build our nice models. Okay. Then this typically is either guided or followed by an evaluation, which is very important for you know, build the trust of our end users on our models. And finally, when hopefully everything is okay, we have deployment and reporting, which is also, you know, very important in terms of properly, deploying your models for end users that most of the times will not be, very technical. There will be, normal, let's say, end users, and also reporting to our customers or clients. Okay, so modeling typically, is where people spend more time on these courses because you have lots of steps where you can fill in lots of slides. Okay, I'll try to talk a bit about other steps, but of course in these 3 hours I don't have time to go through all of these important stages of a data mining project. Okay. Anyway, the plan is, actually start by the end of this diagram, start by reporting, which may be a bit awkward, but the idea is that I think that what I'm going to talk about in reporting may actually be useful for you immediately during this course, because you can actually put it in practice and, document whatever you do during these 3 hours in the tool that I'm going to talk about regarding reporting, and that's why I decided to put it in the beginning. Okay, so then we'll talk a bit about data manipulation, and of course, as I mentioned before, I'm going to assume that you all know R. Okay, I'm not going to assume that you are, experts in R, but here I'm going to delve, very quickly into data manipulation, and of course I'm going to assume that you are reasonably comfortable with R and main R data structures. Okay, so here we are going to talk about some operations that are very handy in terms of data preprocessing and things like that. Okay, then I will eventually here we'll do a very short break, and in the second part I would like to talk a bit about visualization, which is one important part here on the exploratory analysis of the data, and finally address a bit of predictive analytics, which again is important for many applications. Okay, so that's the general goal. Again, I'm sure that this is too much for 3 hours, and moreover, because I will try to stop some of these parts and give you some time for some hands-on, so that this it's a bit more interesting for you, because you put your knowledge to test, and also to let me rest a bit. Okay, all right, so all of this material is on this web page that I have prepared for this course, that you can, I think you were informed beforehand, and this web page is actually here. And so the idea here is that not only you have some basic information on the plan that I just outlined, but also some useful information, some sites which are important for you, some of the packages that we're going to use. But the most important is this part here, this section on course material. So here, introduction will lead you exactly to these slides that I've just shown you. And the other parts are the parts which I'm going to talk during the course. This one, importing data, you may have noticed that it's not here, because actually I'm going to skip it, but I thought it would be interesting for you to have a kind of, as a kind of text, a kind of manual of how to import data in several formats into R in case you need, or in case you are not aware of. Okay, but I'm not going to explain that, but it's in case you need to import some data, either from a spreadsheet or from some text file, then you can have a look at these slides and see if that helps you. Otherwise you can contact me. Okay, so but then the rest are the parts that I'm going to talk. For each of these parts, if you click, you'll see here a link to the slide handouts that I'm going to show, but also all the R code in the slides. Okay, so you have here all the R code that you can copy paste from here into your RStudio console. Okay, so that's more or less the idea. And here you have some bibliography, some of the books. Most of them are free except mine, which is not free, but you have here some links on this part. Okay, so that's more or less the idea. So let's move quickly to the next slide set. So let me just change to the second slide set. Just bear with me while I'm opening my slides. I don't know why I'm having this problem for ages, but my Mac, whenever I'm on these Teams meetings, just scrolls. I don't know when, I don't understand why, but it's just so slow. It's embarrassing. It's trying to open a file, sorry, but it's not my fault, it's just this. All right, so I think finally I have here the reporting slides. Come on. All right, and now let's put this on your screen. Okay, all right, so the first part, as I mentioned, is going to try to teach you something about reporting, okay? Having difficulties here on my screen. All right, so the typical standard process of data analysis involves more or less this step. So we start normally by importing data into our favorite data analysis tool that I hope, if not now, at least in the end of this course will be R, like mine. And then we, we go into this tool and we carry out a series of data analysis steps, model construction, and so on and so forth, until we are happy with our analysis. And then finally we build a report. It can be, either really, a document, or it can be a presentation, some sort of document that reports what we have done. Okay, and now normally this reporting is separate from the analysis part, in the sense that we typically use a different tool for the reporting. We may be using Word for producing our report, or PowerPoint for producing a presentation, but typically this is a different tool from the tool that we used for the analysis, okay? And that means that we normally we are going to be, copy pasting things from the analysis tool into this reporting tool, okay? And so this copy pasting normally is manual, and will of course have the danger that we make some sort of mistake during this thing, okay? And moreover, frequently when we produce some report, and present it, for instance, to the client, maybe they ask us for some changes and things like that, and so this process typically tends to be repeated or iterated, okay? Now this process has several dangers, and I took this from this book. This list is strongly inspired by this book. Okay, so first of all, as I mentioned, it involves too many manual steps, and of course that has a great potential for human error. It involves, for the same reason, too much human effort in terms of time, because we have typically repetitive tasks and boring, because going to a menu, copy paste, changing a window, all of these things, if it's being done for many tables, many figures, it's boring for us humans. And so moreover, because this is heavily dependent normally on user interfaces, it's not easy to record for future reuse. And moreover, small changes in, for instance, the initial data. And I can tell you a story that once I had a project where we were analyzing some surveys, and after we were already like 3 weeks in the work, and the client came with another bunch of surveys that were forgotten or were late in being sent to them, and we had to in a way to start from scratch. Okay, so changes in the initial data set may require repeating the analysis, and of course then repeating the reporting, okay? And so the main source of problems of this, as I mentioned, lies on the fact that the analysis and the reporting are being carried out on separate tools, okay? And so this is the main source of problems, okay? And so, moreover, it's very hard because of this to share the work with other teams, or even to reuse our work in terms of reporting on similar projects that we may have in the future. Okay, so this is the standard reporting process, and these are some of the problems of this standard process. So what I'm going to try to convince you is to change your way of reporting into this idea of dynamic documents. Okay, so this is something which is not related or specific to R. So this idea of dynamic documents exists for a long time. But the idea is that dynamic documents mix the data analysis steps with the descriptive text that we use in our reports. Okay, so these dynamic documents are executable by a computer program, which in our case will be R, and it's this computer program that will produce the final document, the final report. Okay, and so it's not manual, it's something run by a computer program, so there is no space for the usual errors that I mentioned before. Okay, so that's the idea. So this final document is produced by this computer program, and based on the initial document that us analysts create. Okay, and this initial document contains code with data analysis steps and descriptive text, and this computer program transforms this code into actual outcomes to produce our final report. Okay, our final report. Right. So dynamic documents, as I mentioned, are not specific to R, but in R we have this knitr tool that implements this thing. So the idea in this framework is that we have a dynamic document that, as I mentioned, contains both text that we simply write, like if it was a report, and also R code. Okay, and they are mixed together, and this tool will then receive as input this dynamic document and will replace the code by the outcome of this code, which might be table of results, it may be plots, whatever. Okay, and so this is the final document, the final report, and it was produced without any copy pasting between the R and our final tool. Okay, so that's the general idea. Now the idea is, in effect, as I mentioned, rather old, and it's related with the old concept of literate programming that was created by Donald Knuth already a few years back. Okay, so the idea is to implement this in 3 steps. First, the tool inspects the dynamic report and separates the data analysis code from the descriptive text. Then it executes this code and stores the result of each of these code chunks. And then it produces automatically this final document, replacing the code by these results. Okay, and so all of this is done without any human intervention. And as analysts, we simply work on these dynamic documents. We never touch these final documents. Okay. By the way, out of curiosity, these slides were created like that. Okay. All right. So in R, we have several implementations of this idea for different input and output formats, but we are going to focus on this knitr tool. Okay, so this knitr uses as source documents as input documents, these dynamic documents, one of 2 hypotheses. Okay, either to write the text in Markdown, which I will explain what it is, and then have R to implement the data analysis steps. Or instead of Markdown, you can write the text of the report in LaTeX and then put in the middle of LaTeX R code. Okay, so which was, by the way, the case of these slides that you have seen, that they were produced using this schema. But we are going to focus on this because it's easier to explain Markdown than in LaTeX in case you don't know. Okay, so then this tool knitr will be able to pick this single source document and output it in many different formats. It can be a PDF, it can be a Word document, it can be a PowerPoint presentation, whatever. It can be an HTML file. So from the same single source dynamic document, you can produce different output formats. Okay, so that's the idea. All right, so Knitr is then a platform that allows, using different dynamic document input formats, as I mentioned, either LaTeX plus R or Markdown plus R, and then produce output documents, which are going to be our final reports on different formats. Okay. Now, on this short introduction, I'm going to focus on this part, as I mentioned, that mixes Markdown with R. Okay. Right, so this is all based on this R Markdown package that you should install before you try whatever I'm going to show on this slide set. So R Markdown is this package that allows this integration between R and Markdown. Okay, so it's actually includes several tools like this PenDoc, which is a kind of Swiss Army knife for document format conversion, and also includes ways of interpreting R Markdown, which is a literate programming approach that allows embedding R with Markdown documents. So Markdown is a very simple markup language, which was initially created with the idea of making it easier to produce internet pages. So it's simpler than HTML, but the idea is similar. So it's it's a markup language like HTML, and but it's supposed to be lighter in terms of syntax. But it was originally designed for this purpose of producing internet content. Okay, but we are going to use it on a different context. So very brief introduction to Markdown. Of course, there is much more to say than what I'm going to say here. So you can write Markdown as a simple text file. So you need no software, no special software to do this. So you can use like Notepad, your favorite text editor, or you can use the RStudio editor too, because it's a simple text file. Okay, so you don't need any special software too. So it's just text. All right. Now, formatting is carried out with kind of annotation tags like HTML. So, for instance, surrounding a word by these 2 stars in the beginning and the end will make it appear boldface in the final document. A single asterisk will create italics. You have here the idea of some of these markup tricks that you can use to format your report or presentation. Okay. Now you can also use simple tags like a hashtag to create sections and section addings. One is adding one. This is second level adding. You create all sort of these formatting effects with this very simple notation. You can also create like items by simply indenting and using one of these characters to denote a different item, and then this will be translated to the figure that you see here on the right. So all very light in terms of syntax. You can also include links by surrounding the text that will be clickable by square brackets and then putting the URL, and so that will this text here will be clickable and will point you to this web page. You can also include in a similar way images like you see here. So all of these are very basic things that you can do, and actually you don't need to memorize this, because if you are on RStudio, for instance, you can go here on help, and you have here Markdown quick reference, and it shows you most of these things. Okay, some all these things that I'm saying, italics, bolds, and so on and so forth. You have here by just going to help and Markdown quick reference. Okay. All right. So you can also, as I mentioned, you can embed our code within your document. Okay, so that starts to become more interesting, because till now we were just talking about formatting the text, but as I mentioned, the main advantage is that you can embed our code into your document. So how do you do that? You need to tell Knitr that what follows is our code, so it should not be put in the final document if you don't want, of course. and that is, indicated by this beginning of our code and end of our code kind of text. Okay, so this is the way to surround what we call a code chunk. Okay, you start by this, and then everything that you put between this first line and the last line is supposed to be our code. Actually, you can use other programming languages, but it is this R that tells Knitr that what follows is our code, but actually you can also use other programming languages, not only R, but of course here we are going to focus on R. Okay, so that's the idea. You can include our code here, and there will be some options which we call code chunk options that I'm going to explain. But what it does when Knitr sees this document is that the text is going to appear like this. So this is a first level adding, so it's larger. Then an histogram of variable can be obtained with, okay? And then this, instead, in this case, I wanted the code to appear also, but you can, of course, hide the code in case the report is, targeted at, some customer that doesn't want to see our code, so you can hide it. But then our code generates an histogram, and what you see here is the plot of the histogram without you having to copy paste between R and the document. That is automatically put there by Knitr. Okay. Now, as I mentioned, code chunks have options, and so in R Markdown they are indicated by this beginning and end. You actually don't need to type that, because in RStudio you have a button, insert code chunk, that writes that for you. And so, as I mentioned, everything between these two lines will be executed by R. Okay. You can also put code in the middle of the text. Okay, and you do that by this, by putting this backtick, then R, and then some R expression, and in the final document this will be replaced by 4, because that's the result of R executing this. Okay, this is of course a very stupid example, but that's the idea. So you can have inline code in the middle of your text. For instance, you could say, well, you could be writing a report where you were analyzing a data set and you wanted to tell the reader how many rows the data set contains. So you could say, my data set contains, and then instead of writing the number of rows, it would be much more clever that you put something like this. Actually, I'm going to change to R. If you put something like this, and then you put R, and then n row and your data set name. Okay, because this, would be replaced on a R Markdown file by the concrete number of rows of this object, this data frame. And if the data frame changes, you don't need to touch your report, because that will be reflected. Because if instead of 100 rows, let's suppose you added 5 more, then the report doesn't need to change, but the text that appears on the final report will be 105 instead of 100. Okay, so that's makes your report more general. Right. Okay, so code chunks, as I mentioned, have options. Without any option, like this one here, okay, this doesn't contain any option, just tells Knitr that it is an R code chunk. Without any option, the code inside the code chunk is executed. A code block is added to the document showing the R code, and a results block below the code block is also added with the results of the executing the code. Okay, now that's the default behavior. You can change that. You can, for instance, decide to hide the code or just show the code and not show the results. You can just simply mix all these defaults. Okay, now some of the options that allow you to do this, for instance, Eval, that by default is true, allows you to control whether the code in the chunk is to be executed or not. You can simply put code and you just want to show the code. You don't want R to execute it. So you could say, eval false. Okay, so this will show, the code will show up in the final document, but R will not execute it, which in this case, it means that it will not produce an histogram. Okay. Now, echo is also an important option that by default is true, but it allows you to hide R code from the final document. Okay. And you do that by, putting echo equals to false. Okay. So that's, two of the most important, but there are several other options or code chunk options that you may wish to explore. And here there is a web page with a list of all of them and, an explanation of all of them. Okay. Now, some of your code will tend to generate figures or, plots. Okay. For instance, this code here, if I write this, assuming that this is the famous iris data set, will produce in the final document something like this. Notice that because I don't have any options, it will have two results: the code and the outcome of the code. Okay, so that's the default. Show the code and also the outcome of the code. Okay, which in this case is this plot that you see here, which is the result of running this. But again, note no copy pasting involved here. Okay, so this is done automatically for you. You can also, insert tables on your document, and this function from the package knitter is handy because it allows you to format the tables in many ways, add captions and all of these things that you tend to like to do on reports. Okay, there are many options.
Hey, as in, I've had this stuff for quite a while, and I didn't even use it. This,
sorry?
Samsung buds.
Yeah, go ahead.
Okay. What's this one again?
You have a question? Oh, okay. All right. So, this cable function is handy because it allows you to produce tables in a nice way on your report with lots of formatting options available that you can explore on the help of this function. Okay. Now, to generate the final document, you have a function which is called render that takes the name of your dynamic document. Typically, we tend to give the extension RMD for R Markdown to our dynamic documents. And of course, the name is whatever we want. And so if I have written this report, let's suppose, if I want to generate the output report, I can just load the library R Markdown. Of course, that assumes that you first install it. And that installation is only necessary once. Then you can load the package and then you just call render, which is a function from the package, apply to your dynamic document, okay? And that generates the output of your report, okay? Now, the type of output that is generated can be controlled by options of this function, or it can be controlled in the document in itself. So in the dynamic document, I can have a kind of header, a kind of metadata information where I put, for instance, the title of the report, and also I can control the output that I want to generate. So in this case, I'm saying, well, I want a PDF as output, and I want a table of contents, and I want to use some sort of, a formatting style for highlighting the code and so on and so forth. So that's all possible by putting a kind of preamble on your dynamic document. In the beginning, you have this kind of metadata information, okay? Now, much easier than that is to use the interface of RStudio, okay? So instead of showing you these slides, let's create here one report. So let's create here, so if you go to File, sorry, I'm going, if you go to File and then you create a new file, R Markdown, then there is a user interface that allows you to fill in, for instance, the metadata information. So, for instance, the title of your report, It allows you to put the author of the report, and it allows you to define the output format. You can change later on. No need to worry about having to make this decision from the start. You can change, but you can already select a default output right now. Okay. And notice that here you can also select among documents or presentations or other things, and that depend on the package that you have installed. But at least documents and presentations you have available. Okay. So let's try to click OK. And what our sudo will do is to show you a kind of template of a document. Okay, so you can simply delete this. Of course, these are it's just a generic template. But here the header is whatever you answer to that graphical user interface. So the title, the date was added automatic, and the output format that I decided to use. Okay, so you can of course change this. And of course, you can also delete this template and write your own report, okay? So once you are happy with your report, if you want to generate this, as I mentioned, you can either use the render function, once you save your document, of course, or you can use this button here, knit, okay? And actually, if you click on this arrow, you can change the output. So you can change from the default that you have selected, which is HTML, but you can say, well, now I want a Word document, and you just select this option without changing anything on your dynamic document, okay? And so that will do the magic. Of course, if I type this, it will ask me to save the file. So let's be a bit, untitled, it's okay. And once I save the file, then it compiles the dynamic document here, and it will produce the report, in this case in HTML file, okay? It should appear here on a window, yeah, very good. Come on. Anyway, you see what I'm getting. You see the report finally when my computer decides to run it. Okay, so you see here. So you have here second level header. Then you have here a link. Then you have a code chunk that is being used with the default. So it shows the code and the results. And here another code chunk that is plotting something, but with echo false. No code is shown, just the plot. Okay, so again, this is just an example. Of course, you can write your own document. Okay. All right, so let's continue and try to make this a bit more interesting. So that's what I was saying. Okay, so as I mentioned, there are many types of output documents that you can generate with this idea of R Markdown and dynamic documents. Okay, so they can go from HTML to PDF, Word, open office documents, R manuals, vignettes, presentations in different formats. You can also create dashboards. You can create websites. Actually, this website was created with R Markdown. I wrote 0 HTML for creating these menus and all this stuff. Okay, all of this was done with R Markdown. Okay, so you can create books, you can create journal articles. Lots of journals nowadays are providing templates for their own format for R Markdown. For instance, there are a few packages that some of them I have installed. But when you install these packages, here from template, I have several of them installed. And for instance, you have here like IEEE transactions journal. This package contains formats to generate, as output from a R Markdown already a journal paper. Journal of JASA, lots of journals are already creating, templates for their own formats, Elsevier journal article, many things that are available by installing extra packages. And these articles is one example that contains, lots of templates from for different journals. Okay, just as a side note. All right, so another thing which is strongly related is this concept of R notebook. So an R notebook is a type of R Markdown document, okay? So it's written in R Markdown, okay? But they are a type of R Markdown with a special output format, which is this HTML notebook, okay? And so the main characteristics of these R notebooks is that the code chunks can be executed independently of each other and interactively. So I can, instead of compiling all the document, I can just run a part of the code in an interactive way. So R notebooks are really nice for you to document your work with R. And actually, I recommend that you do that during this course, that you create an R notebook and take your notes with your comments and eventually include text. So you could come here, file, new file, R notebook. That a template should appear here, okay, on the editor, and you can give it a title. So data science with R course, whatever. And you can, write your own comments and include, this is my first exercise, whatever. And, if you want to write some code, you come here, you insert a code chunk, okay? And then you write your code here, let's say data, iris, whatever. Okay. And you document, you include code and text, okay? And as I mentioned in our notebooks, if you want to execute a part of this, you can simply type here, click here, sorry, and this is executed, okay? You see, and it's executed here, okay? You can hide the output if you want, but you have this kind of interactive, yes, I think there is a question. I see a hand, Joel. Yes, I think you were the first.
I was just wondering, how'd you do the thing where it inputted automatically the start of the code chunk?
It's here, insert. You see here, this
okay.
button. And then if you click here, it just allows you to select different programming languages, but you can select R, and that's it.
Okay, thank you.
You're welcome. There is Mary also with a question, I think. Mary, you are muted, so I'm not. Yeah, now not.
Sorry. I wonder in R we don't need to define our data set format, like if it's CSV file or Excel sheet, because you just directly said data that.
Yeah. So that has to do with that part that I'm going to skip, data importing. But this instruction here is a function in R, which is this function is called data, that allows you to load data that already comes with R, okay? So I had no need to import it from any external source because this is a data set that already comes with R, okay? So in case your data was in an external source, for instance, a CSV file or a spreadsheet or something like that, then you would need to know how to import that into R, okay? And those slide sets that I'm going to skip, but I have on the web page, will give you more information. This here, importing data, it will give you more information in case that's your problem. Okay?
Yeah, thank you.
You're welcome. All right, so our notebooks then I think are very handy for documenting our work with R. Okay. Now this is an example already shown, and this is also shown how to create one using the user interface on RStudio. But once you save an R notebook, there are two files that are created. Okay, one which has the extension RMD, which is the standard Markdown file, and another one which is an HTML file. Okay. And this HTML file contains the output of the report, and it can be opened on any browser, okay? Now, our notebooks are also nice to share your work with your colleagues because you can send them either the two files, or if it is a non-technical person, you can simply send her or him the HTML so that it opens on our browser. Or if it is a technical person, you can send the HTML, because the HTML file contains embedded the R Markdown file. So instead of sending the two files, it's enough to send the HTML file that, once you open it on RStudio, it automatically extracts the R Markdown file. Okay, so it's a nice way to share your work with others. Now, more interesting is to use this concept of R Markdown with parameters. Okay, so why is that more interesting and powerful? So sometimes we need to produce very similar reports for different subsets of our data. Okay, so suppose that we regularly need to produce structurally similar report for sales of a company, but using data from different countries. So the structure of the report is the same, but the data is different. So it would be nice to to avoid having to create all of the reports for each of these subsets. Okay, and that's the idea of the power of this R Markdown, and particularly with in conjunction with these parameters, comes exactly from that. Okay, so we can create a dynamic document that contains parameters. Okay. And changing the value of these parameters will change the output of our report. Okay, and this is done through this params field on the header of the document. Okay, so let's see a concrete example. Okay, let's suppose that I want to show the codes of a stock of some company for the daily codes of the stock for the last X days. Okay. So you may be familiar or not that there is a package in R QuantMod that it's an extra package that you need to install before you try what I'm going to show. But this package has lots of functions to play with financial markets, and one of them, which is this get symbols, allows you to fetch data from Yahoo Finance. Okay, and then this candle chart allows you to show the data in a nice way. So let's see an example. And again, to try this, you need to install this package before. Okay, so let's see an example. So let's start by loading the package library QuantMod. Okay, and now let's try to fetch some data using this get symbols function. Let's say from Tesla. From, let's say, 2021-01. I'm going to explain this in a minute. Okay, so what this has done, so let me show you the first rows of this data set, is that it went to Yahoo Finance and it fetched the data, the daily codes from Tesla, starting on the 1st of January, actually because it was holiday, it only starts on the 4th of January. And, for each day, it has the open price, the highest price, lowest price, the close, the volume, and the adjusted close, okay? So, this data, of course, I'm just showing you the first rows, but you can then plot this data with these nice, professional plots that show you these candle charts that show you the evolution of the price. But, forget about the meaning of that if that is very awkward or strange to you. But the idea is the following. So let's suppose that I want to do this for different companies. And eventually, even for different days, maybe I just want the last 7 days or the last 2 weeks or the last 3 months. So let's suppose that I want a very simple report that, fetches the data and shows such a plot for any company, any number of days back. Okay? So, and I want to be clever in the way that I don't want to write many reports. I want us to write a single report because the structure is the same. Okay? So, one idea then is to use these parameters. So I have here the solution. You see here, this is a Markdown report. Okay, it's producing HTML, but it could produce anything else. Then I have here a code chunk where I define two variables. One that I call ticker, where I will store the ID of the stock. In this case, I put April. And then I have another variable that I call end days, where I put my decision on how far back I want the codes, okay, from today, of course. And then I could produce, I could write the codes of, and here I put the content of this variable. So that means that if I put here another company, then the report changes, okay? So this will show me the codes of April for the last 30 days. But if I change these variables, the text changes on the report, okay? Then I have another code chunk that, I'm not going to show the code. That's what this include false does, okay? But it loads the package, fetch the data like I did here, but it's a bit more clever because the from, instead of being fixed like here, it's today, because this function gives you the current date, okay? Right, today less end days, which is in this case 30 days. So from this date till today, okay? So that's essentially the same code, but being generalized with these two variables, okay? And then I produce this graph, okay? So if I compile this, so if I iter on this, I will get a web page that will say the codes of April for the last 30 days. So finally, my computer will output that. Okay, so yeah, all right, so you see. But if I change to another company, I will get a different report. And if I change to, let's say, 90 days, I'll get a different report with a different plot and so on and so forth, okay? So that sounds already interesting, but it's not the only thing that you can do. So let's move back here. So that's what I was just showing to you. But what you can indeed do is, you have different ways of using the flexibility of those variables, okay? You can change the markdown here by changing the ticker, okay? But that's not very interesting, okay? And actually, I was being a bit lazy here. Instead of specifying the variables, oops, sorry, like I did here, what I should have shown you, actually, it's this. That contains the same thing, but as parameters, okay? But it's the same concept, okay? Forget about this show code. But the idea is that I can specify values of variables instead of this, like I did here, which was a bit, rudimentary. I can specify them as parameters of this report. And what's the advantage of that? Of course, the advantage is not allowing me to do this, change this here, because that I could already do here. So it's the same thing. That's no advantage. But the advantage of specifying the values of these variables as parameters is that you can call knit with parameters. Instead of knit just, you can select knit with parameters. And what does that do? It pops up a graphical, a dialog box that allows you to fill in the values of the parameters. Okay, so I can go here and say Tesla, and I want 60 days. And this show code parameter is whether I want to show the code in the report or not. So let's suppose I want to show the code. Okay, I click knit and I get a different report, different from what was here. Okay. So please note that the way that we use the variables is slightly different from this, okay? While here I was just referring to the name of the variables, you see here. Here, because they are not variables, they are parameters, I need to refer to them like this: params, ticker, params, and days, and so on and so forth. Okay, because these are, this is actually implemented as an R list. Okay, but you see, I got here, and note that I was generating PDF, so I got a PDF file. That's why it's appeared as my PDF viewer, and it's showing the code because I said I want to show the code, but it's for Tesla 60 days and not what was here. Okay, so you can actually once you use these parameters, you can actually run Nita with parameters, or you can call the render function where you specify different values of the parameters that change what is in the report. Okay, and that is actually powerful because let's now suppose that my company asks me every day to produce such a simple report for, let's say, 10 stocks. So if I'm clever enough with this, I can actually produce that, just by clicking a button. Why? Because I can use this render and I can create a script, okay, where I have a vector with the names of the stocks for which my boss asks me to produce a report, okay. Then I have a loop for each of these stocks. I call render on that flexible dynamic document, but with a ticker parameter set to the value of S, and S will be Microsoft, Apple, Tesla, CRM, and Alibaba. Okay, so that's very flexible, and you can, just by running this, you can produce all the reports. In this case, I'm producing as an HTML file. Okay, and imagine if instead of 5 companies we had 100 companies. That would be lots of work to do that by hand. But just by having the tickers of the companies over there, you can simply run this report with different parameters. In this case, just by changing the company name, and just with one single dynamic document, you can produce a huge amount of reports. Okay, so that's the power of having dynamic documents with parameters. Okay. I don't know if you have any question on this. I mean, that's the end of this reporting. I have here a few links with more information, but I don't know if you have any question on this. If this was not clear, I have here the script. So you see here, if I run this script, let me see if I am on the right folder, otherwise I will generate this. Let me change to this. Okay, so if I run this, sorry, if I run all the scripts, sorry, so it fetched the data, it's fetching the data and producing one report, one after the other. Okay, so it did the first one, probably. So now it's producing the second one, and it goes on for all so it's producing the second one for the second company, Apple. Then it will produce the third one, and so on and so forth. Okay, and in the end, on the folder where this is, which is actually here, you will have the HTML files of all the companies. Okay, and that with this simple code and one single dynamic report. Okay, so that's the power of this dynamic reports. All right, so while this is running, yeah, Danny, yeah.
Just wondering, Louis, is the list of RMD files that you're showing there, are they accessible from the? Are some of those examples in the course material, and I'm just not seeing them?
These ones, no, but I can put them. Yeah, indeed. Maybe I should add. I mean, they are here on the slide, the code, but it will be more practical if you have the if you indeed have they are here, you see, but instead of you having to type this, I can put them on the web page. Okay.
Yeah, I have been trying to cut. I've
Sorry?
been trying to paste some of the things in, but unfortunately, from the slides, it kind of messes up the the line feeds and everything like this. It doesn't kind of translate.
Okay. From the slides, yes, but from the web page, I think maybe you can have here the code in a more manageable way. Our code of the slides. Yeah, but this one, yeah, it doesn't contain the documents. Yeah, you are right. So I'll put them here, okay?
Okay, thank you.
You're welcome. All right, so let's move to the second topic if there is no more questions. Then maybe you can lower your hand, otherwise I think that you have another question. Okay, so let's open the second. As I mentioned, I'm going to skip the data importing slide set because I don't have time as expected to talk about all of this, but you can later on, if you have any questions on that, contact me, okay? But I'm moving into data manipulation, which is opening right now. All right. Okay. All right, so this slide set is about essentially one package, which is dplyr. Dplyr is a package that really greatly facilitates manipulating data in a consistent and very powerful way. And I recommend that you do most of the operations with dplyr instead of using the basic facilities in the R language through the standard data frames. Okay. Now, dplyr is a package that has several interesting features, like it implements most of the basic data manipulation operations that you see on database management systems, for instance. So you can have access to them, similar operations here in R. It is able to handle different data sources, so you can have a code which stays the same, but you can change the data source. So you can, for instance, change from a database to another database, and or to from a database to a standard data frame in R. The data source is removed from the code. And the code in terms of operations of manipulating the data stays the same irrespectively of the data source, okay? And moreover, it is very fast on these operations, okay? Now, dplyr defines a new class of objects, which is a kind of superclass of the standard data frames that R comes with. So a data frame, as you hopefully know, is the standard data structure for storing data in R, and dplyr defines these civil objects, which is a kind of generalization of a data frame. Okay. Now, one of the things that it does, it sort of encapsulates the possibility of the data being stored in different sources, not only on a data frame, but it could be on a remote database, for instance. Okay. But you just need to tell dplyr in the beginning, what is your data source? Is it a data frame? Is it a database? If it is a database, in which server it is, what is your username, what is your password to access that. And once you do that in the beginning, then the rest of the operations are the same, irrespectively of the data source, okay? So that's very powerful because it allows you to generalize your code, okay? So for instance, if you want to do manipulation operations over a standard data frame that comes with R, as I've shown you before, by doing data iris I kind of load a data set that already comes with R. And so after doing that, we have a data frame, which is named iris. And then I can say, if I want to use dplyr over this, I can say, well, generalize this as a table, which is this special data frame created by dplyr. Okay, and so I store this table, which is actually it doesn't copy the data. Of course, that would be very silly, but it's a kind of link to the data frame. So in this case, the data source is a standard data frame, which is named iris. And now I'm connecting dplyr to this standard data frame through this function as table. Okay, so from now on, I will only use or refer to the data through this object IR. Okay, so the first thing that you see as different is that if you type the name of the object, it will not show you, or it will not dump on your screen all the data frame like R does on a normal data frame. So if you have, let's say, a data frame in R with 1 million rows and 100 columns, if you type this, then your screen will be dumped with information. Okay, so tables are a bit more space aware. So it will show you in the beginning what are the dimensions of the data, and then it will show you a kind of glimpse of the data, the first 10 rows and some of the columns. Okay, you can of course see all the data if you want, but that needs to be asked on purpose. Otherwise, you incur the danger of flooding your screen with lots of data. Okay, so that's one first thing. You can of course see also other information like the data type on each of the columns, which the standard data frames do not show, and things like that. Okay, but of course that's not the main advantage of tables over data frames. Now, as I mentioned, one advantage of dplyr is that you can query data on different data sources, not only data frames. Okay, for instance, you can play with data that is stored on a relational database. Okay, for that to be possible, of course, you need to install extra packages that teach R how to communicate with these relational databases. So, for instance, this package, does the translation between dplyr and vendor-specific SQL statements. And then there are packages specific for each of the database management systems that you may wish to interface. This is just a sample of the available packages, but there are more. Okay, but this is out of the scope of this course. But just be aware that you can have as a data source not a data frame like here, but a relational database. Now, I think I even have here an example. Okay, so this is a very naive example where I'm creating an object. So these sensors is a dplyr table like this IR. Okay, but this IR is connected with the standard data frame, while these sensors is connected to a database on a server that contains some values. Okay, so this is the code to connect R to a MariaDB, that is on this server. Of course, this is all fake, of course. And on this server, there's supposed to be a database with this name. This is my username on that server. Then this will ask me for a password, and provided that I'm okay, I have the credentials, then I can connect this object with a table on this database named sensor values. Okay, and from now on, I forget about this database and I work with this object sensors exactly with the same functions that I will work with this IR. So that sort of generalizes the data source. We only need to bother about that in the beginning, where I tell dplyr where is my data. Is it in a data frame? Is it on a remote database? Wherever. And once I establish this connection, then I can work with this object like, if it was a data frame. Okay? So that's one of the advantages of dplyr.
I was just put up my hand for a second.
Sorry.
One of the things I'm trying to grok is I've been doing a study with Fitbit. And so, you can have the regular export of the data, but really there's a way to call the data from a specific device, and you get this, you know, these security tokens issued, and then you have to pull with JSON data from that user. And I got as far as being able to, you know, make the connection, but you know, kind of got stalled out on pulling the data. And so this is something I'm going to come back to, but maybe this would allow that.
So, I mean, of course, I'm lacking lots of details on your specific example, but from what I understood, I think you are able to get the data on a JSON file, right?
Yeah, using the JSON format.
Yeah, so R has packages to read JSON format files, so that could be an hypothesis. But of course, that would not be the same thing, because what you would probably want is to leave the data on the device and just fetch the data as you need, not, you know, fetch all the data, unless it's not a very large data set.
I mean, I would be interested in fetching like large amounts of data, and it does seem to be where I got stalled out, and you know, it's because I had other stuff to do, but was, you know, I was able to make the connection and get the security tokens to work, which is like this whole process where people consent to sharing their data. But then I guess I needed to actually, I wanted to formulate a JSON query that would actually grab all the data, and I just kind of ran out, you know,
yeah,
energy there.
So, I mean, what I can tell you is that if you search on the web for JSON and R, you will be pointed to a package. I think it's named RJSON. I'm not 100% sure. Let me check here. I don't think I have it installed, or maybe I have. Let's see. So let me see if I have it here on my packages, because I install lots of stuff. Yeah, maybe it's easier here. Yeah, you see, there are several packages. At least these two probably will help you. So have a look at the documentation of this, and probably it will solve your problem. I'm not sure, but that will be my suggestion.
Very good, thank you.
You're welcome. All right, so continuing with this. So now that we have our data somehow linked into dplyr, is there any other question? No. Now that we have the data linked, wherever the data is being stored, either on a data frame or a remote database, whatever, now we can think about which operations we can do with this data, irrespectively, again, on the source of the data, okay? And so dplyr provides 5 basic operations, okay? There are more, but these are the 5 more basic operations. So they are implemented through these 5 functions: filter, select, arrange, mutate, and summarize, okay? So filter is used to show only a subset of the rows. Select allows you to show only a subset of the columns. Arrange allows you to change the order of the presentation of the rows of your data set. Mutate allows you to add new columns as a result of some calculation process. And summarize allows you to calculate summaries of the values of a column of your data, okay? So for those of you familiar with SQL in databases, you know, this will immediately map to some of the instructions that you have on this language, okay? But anyway, let's see it here. So all these operations have the same structure to, you know, be easier for you to memorize. So the first argument is always one of these table objects, okay, these data frame tables, okay? So it will be either this IR or these sensors that we have seen before. And the remaining arguments of the function will describe what you really want to do with the data, okay? So all of the functions return an object of the same type as the first argument, except of course the summarize, because the summarize calculates a statistic, okay? And moreover, unless explicitly told to do so, none of these operations change the data, okay? So there are no side effects, no hidden side effects, okay? So these are kind of the rules of the game of these operations. Now let's go through them. So the first one is this filter, which, as I mentioned, it allows you to show some of the rows of a data set. So let's work with this iris data set. So I'm not sure if you are familiar with this, but probably you are more than familiar. But IR, no problem, is a data set with iris plants, basically 150 plants described by 5 variables. Okay, the first 4 are biometrics of the plant, and then the 5th column is the species of the plant, which is one of 3 possible values: setosa, virginica, and versicolor. Okay, so that just for you to understand. So for instance, applying this instruction to this 150 times 5 data set, it will show only the rows for which sepal length, which is supposed to be one of the columns, is greater than 6 and sepal width is greater than 3.5. Okay, so you can put conditions on the variables, on the columns of your data, separated by commas, and these will be interpreted as logical ANDs by dplyr. Okay, and the result of that would be, in this case, only 3 rows satisfy this query. So if instead of the logical AND you want to do a logical OR, then you need to use the OR operator of the R language. Okay, because the comma assumes that it is the AND. Okay, so in this case I'm filtering, showing only the rows for which sepal length is greater than 7.7 or it is less than 4.4. Okay. Now, the arrange statement allows you to change the presentation order of your rows. Okay. For instance, this will show me this data set ordered by species, and then, if the species is equal, by petal width. So because species is a nominal variable, it will be on alphabetic order, ascending alphabetic, and petal width, because it's numeric, it will be on ascending order, increasing order of petal width. Okay, so in this case I cannot see because there are 5 columns and my slides are truncating that, but you could see that if you run the code on your computer. Okay, so arrange allows you to specify criteria to show the presentation order. Please note that it doesn't change the order in the original data. Remember what I said, none of these operations change the original data. Okay, they just print stuff. Okay, so this change of order is not going to be done on the original data frame. It's just a presentation issue. Now you can also specify descending order using this function. That's applied to some column is descending order, depending on whether it is numeric or nominal variable. It will be alphabetic or numeric. And then the select statement allows you to select a subset of the columns, okay? And they are basically specified by their name. As you can see here, show me only the sepal length and species column, okay? So 150 rows, 2 columns, because those are the columns that I selected, okay? Now you can sometimes, it may be a bit, long to type all the columns that you wish, and there are a few operators that may facilitate your work with that. That is not the case for this data set because it only has 5 columns. So even if I wanted to type 4 of them, it's not lots of typing. But this is just an illustrative example. So you can use this column here to mean an interval of columns. So the meaning of this is from this column until that column. So all of them in between, okay? And then this minus here negates that. So it means all except this, okay? So I'm excluding the interval of columns from this one till that one, okay? So this is negating. This is allowing you to specify intervals of columns. You can also say, well, give me the columns whose name starts with sepal. Okay, and there are many of these utility functions that allow you, to specify this thing. Okay. Now, mutate is yet another statement that allows you to add new columns, and this add should be, in quotation marks, because actually, as I mentioned, you don't actually change the original data. So it's adding on the presentation. It's not really adding on the data. If you want to add on the original data, then you need to explicitly say so. Okay. So in this case, I'm saying, well, mutate this data frame, adding a new column named SR, whose values result from this ratio, the ratio between the value of sepal length and the value of sepal width. Then another column named PR with this ratio, and yet another third column, which actually it's the ratio between these two that I just created. Okay, and so that will be 5 plus 3, so 8 columns. You see here, 8 columns. Actually, it's not showing, but they are over here. Okay, but once again, this doesn't change. So let's see an example. So mutate. Mutate. You see here, this statement generated, it appended a new column here, okay? But the object, the original object, stays the same. You see? So it's still an object with 5 columns and not 6. So if I indeed want to add this, I need to be explicit. I need to say, well, mutate and assign the outcome of mutate to the original object. That will change the object. But I need to be explicit about that, okay? So that's to avoid, unwanted or unintended side effects, okay? Now, sooner or later, when we are playing with data, we will tend to, apply several of these operations. For instance, maybe I want to filter the plants such that I only want to show petal width greater than 2.3, but from these plants, I only want the sepal length and the species. So I want to filter, and to the result of filter, I want to select only these 2 columns. So R, as you know, is a functional language, so I can apply functions to functions, so function composition. And that's what I'm doing. I'm applying the select to the outcome of the filter. And the outcome of the filter is a data table, a table, okay? And that's why I can apply that. And that, of course, can sooner or later be a bit messy. So although I try to put everything on different text lines and try to use indentation, because actually I could have written this in the same line, which would be even messier. But, even though I'm making an effort, it's not so easy to understand what's going on here. Okay, so I'm applying a range to something, which is the result of select, that is being applied to a result of a filter, that is being applied to a result of a mutate. Okay, so actually it's easier to understand what is going on by reading inside out. So the first thing that I need to do is this mutate. Then the result of the mutate is filtered by this condition. The result of the filter after the mutate is selected by these columns, and the result of that is arranged by species and descending sepal length. Okay, so it's not very easy to understand or read, but it's it's the result of a functional language, because you apply functions to the result of functions. Okay, but some people find these very clear, others find it very hard to read. It depends a bit on the way your brain works. Okay, but in case you don't like this, there is nothing wrong with this, but in case you don't like, there is one operator, which is this chaining operator, sometimes called the pipe, that comes to rescue from this nightmare. So this operator, which is basically the percentage sign followed by the greater than and then the percentage without any space, allows you to chain operations. Okay. So what's this has nothing to do with dplyr. Okay. So you can do that to any R operation. Okay. So but what it does, so it allows you to let's suppose that I have this. Okay. I want to apply the function f to the result of applying g to 5. Okay, so that's written in functional language. So using the pipe, I would do the following. So I would put this, okay, then the pipe operator, and then this. Okay, so this is an operator that simply rewrites the expression. So it transforms this into that. What it does is that it picks the left-hand side of the operator and it inserts it as the first parameter of the right-hand side. So for instance, if here I had a number, that would be equivalent to this. Okay, so whatever it is on the left-hand side of the operator is inserted as the first parameter of the operation on the right side. Is that clear? But it's essentially a rewriting, because internally it's transforming this into this. Okay, but it's just for you. If you find this very complex, particularly when you are applying functions over functions over functions, then this becomes, at least for me, more comprehensible. So for instance, this is exactly the same thing as this, but this, you know, in a way I'm writing this inside, as I read it, inside out. So I start by the mutate, then to the result of mutate I filter, then I select, then I arrange. Mutate, piped to the filter, piped to the select, piped to the range. Okay, and so this mutate is going to be inserted here as the first parameter of this. Then the result of the filter is going to be inserted here as the first parameter, and so on and so forth. Yes, Danny?
So can you mix these? Can you put the can you express it in the way that you have above part of it inside of the in between, like the greater than? You can do that. You can mix them.
Yeah, you can mix the things. And actually here, if I'm calling a function here inside of this function, you see here. So.
All right. Yeah. Yeah.
So, yeah, because actually it's just a rewriting thing. So it's not doing anything magical. It's just picking this part and inserting it in as a first argument of that. So whatever else you have there, it's up to you.
Right. Okay. Thank you.
All right. So let's now move into summarize. So as I mentioned, summarize allows you to calculate some metric on the values in a column. Okay. So for instance, summarize this and creating this summary that I decided to call AVGPL as a result of applying the function mean to this column will give you the mean petal length, because that's an R function that calculates the mean of a set of values. Okay. And this one is going to calculate the variance of septal width. Okay. Of course, each of these functions return as one single value, so the outcome will be this, two numbers. Okay. So summarize picks sets of values in a column and calculates some metric, some statistic on these values. Okay. Now this becomes more interesting when joined with another interesting function of dplyr, which is this group by. So group by allows you to create subgroups of your data according to some nominal variables, according that establish some criteria. For instance, I could decide to create subgroups of the plants by species. As I mentioned, there are 3 different species. Okay, so I could just say group by my plants by species. So that actually does essentially nothing. Actually, technically, it creates an index. If you know about databases, it creates an index to make things, more efficient to access. Okay, but essentially, it does nothing. If you type the object, it shows the same data. It's a table with 150 times 5, but there is here an extra row of text that says, well, careful, be aware that this is grouped by species, and there are 3 groups. Okay, so why is this interesting? It is interesting because sometimes I want to calculate these summaries by subgroup. So without this group by here before, this summarize would calculate one single number, which is the mean of the petal length, right, over all the data. But with this group by, the summarize will be, because this, due to the pipe, will be applied to, the summarize will be applied to the result of group by. And so applying the summarize to the result of group by, applying the summarize to a grouped data set, it will generate as many summaries as there are groups. So because species has 3 possible values, summarize will calculate 3 means. 1 for the subset of plants whose species is setosa, another one for the subset of plants whose species is versicolor, and a final one for the subset of Virginicus. Okay? Now, this is much more interesting because it allows you to, to contrast properties of some variables, in this case petal length, across different subgroups of your data set. In this case, it allows me to see if indeed the typical petal length is different across the species. And indeed, we can confirm that, for instance, setosas have a much smaller, typically have a much smaller petal length than the other 2 species of plants. Okay, so that's the interest of this type of grouped summaries. Okay, now here you have a few more examples of using groups. For instance, you can also use groups for counting, not only calculating summaries on the subgroups, but counting. For instance, group by IR species and then applying this tally to the group by, that counts the number of elements on each of the groups, which in this case is 50 for all of them, because this data set has 50 plants for each of the 3 species. Okay, and these are, basically different ways of doing the same exact thing, but it's just for in case you are curious. But actually, the easiest way of doing that is to use a specific function, which is this count, that allows you to say, well, count the rows by species. Okay, that's the easiest way to do that. You can also do things like top and bottoms. You can see, for instance, here I'm grouping by species, then arranging by descending sepal width, and then this slice allows me to show the first 2 rows. And so this shows me the top 2 petal lengths by species. Okay, because I'm ordering each of the groups by decreasing petal length, and then I'm from each of these ordered rows, which will be the 150, but they are ordered and grouped by species. I'm just picking the first 2. Okay, so these are the first 2 that you see here. And actually, there is a specific function for that, which is this top n, that allows you to say, in a more synthetic way, well, I want the top 2 petal lengths by group. Okay. You can also get the bottoms by applying the top n with minus instead of a positive number. Minus, it's the opposite. And in this version, instead of decreasing, I would have increasing. Okay, but it's better to use this top. Then you can also combine data. Okay, and I don't have time to do that, but functions like bind rows, bind columns can be used to glue tables either row or column wise respectively. And finally, if you work with data which is spread over different tables, for instance in a database, you have operations like similar to the ones that you have on database management systems, like the join, the left join, right join, inner join, and full join that complete similar operations like the equivalent in SQL. Okay, but that's just for basic information. You need to search for more information on that because we don't have time for going through that. Okay, so that's some further information that in case you want to know more about dplyr that you may wish to consult. And now what I would suggest is that we stop a bit and you try to practice some of these things with by doing these 4 exercises with dplyr. Okay, so for this to be possible, of course, you need to have dplyr installed, which I hope you already have. Otherwise, I can help you. And in this specific case, because we are going to use a data set that comes on this package, this is also an extra package that you need to install. Okay, so for this you need this package MLbench and this package dplyr. Okay, so this package essentially contains data sets from this UCI repository. Okay, so once you have the 2 packages installed, you can load them, and then you can load the ozone dataset from this package. I can eventually do that for you just to speed up because we are running out of time as expected. And so assuming that you have already installed the packages, to load the ozone data, you can simply do this. But this will only work if you install the package before, okay? All right, so now you have ozone, which is a data frame with lots of things. You see, that's the problem with standard data frames. But of course, what we want is to create a dplyr object from this. And so let me just put the instruction here again in case you want to copy it. So, and then you can load dplyr. And then what I would recommend is that you create an object, let's call it OZ if you want, which is a link to the data frame. Okay. Okay, and this object, it is a bit more manageable, and you can see that it is 366 rows and 30 columns, and you can see immediately that there are a few unknowns here, which is the meaning of these NA values. Okay, so once you have done that, you have the data set, and you can try then to answer these questions. Okay. So I'll leave it here. Probably I will leave it here for a while in case you want to copy these instructions, because the slides you have access, and then I will change to the slides again. Okay. Once again, before you need to install the packages, okay, which is only done once, but you need to do that. So in the interest of time, maybe we can do the break now while you are trying to solve this exercise, and because we are actually running out of time, so we can do a short break if you want to drink some water or something like that while you practice. Okay. So there is a question, I think.
So I guess the column names are like V1 through V13 instead of humidity.
Yeah, so what you can do, you can know more about it. So you can call help. Oops. Why is this? Yeah, oops. So here you see what is the meaning of the columns, okay? So if you type help ozone package, and so now you can know which column, you can actually rename them if you want. So you can say, well, call names, ozone is something if you wish, or just memorize which one is the humidity and so on and so forth. Okay.
Yeah, so number 7 is humidity.
Yep. Then you want to ask some question? You are unmuted. I don't know if that's intentional or not.
No, I had a question earlier, but you answered it actually along the way. The big thing about Dipler is just that it makes it easier to manipulate the data frame, right? And then
yeah, that's
not
only that, but also encapsulating the data source is also relevant, and it's faster than the standard data frames.
Right. Underneath, it's still data frames, though, right? It's not actually a new data structure.
And not necessarily, because it depends on the data source. So if your data source is the database, so it will not fetch all the database, only as needed. Okay.
So can you manipulate images and things like that as well?
Well, that's a different animal. So an image, it depends on how you represent the image. Of course, if your image is a matrix with pixel values, then the idea of this is to play with squared objects like rows and columns. If you can represent your image like that, then of course you can do that. Because dplyr just looks at this as a table of columns and rows. It doesn't know what's the meaning.
Right. Yeah. Okay.
So I did a group by ozone V1, and then I did a pipeline to summarize, and I called it mean humidity. So I think I did it, but there's a bunch of NAs in there.
Yeah, because the data has lots of NAs. So let's see. Let me see what I've done. So the first thing I did was, I just decided to rename the columns because I thought it was a bit more practical. But of course, you don't need to do that. But I just decided to do that. And then that's what I did before. So loading the data and then link dplyr to it. And then for the first one, I did a group by month, and then a summarize apply to these groups. Okay. And the trick here, because of the NAs, is so this has nothing to do with dplyr. Okay, this has to do with the way the mean function works. So let me explain better. So for instance, if I apply mean to this column V7, okay, because it has NAs, as you can see here, the mean is NA. And that's actually what is supposed to be, because if you are calculating the mean of something that includes something which is unknown, the mean is unknown. So that's the correct answer, right? But sometimes you want to still calculate the mean, but ignoring the NAs. And that's something which you have to do to tell the function mean, which is the function in R that calculates means. You have to tell the function, well, look, here is a set of values. I want you to calculate the mean, but ignore any NAs, okay? And then that instead of returning an NA, returns the actual mean, disregarding the values that are NA, okay? And that's what I did here. When I call mean, I added this extra parameter, NA removed true, that basically tells mean, well, look, calculate the mean immediately, but ignore the NAs. Okay. And that's why I haven't got, any NA here.
Okay, yeah, I got it. I do that all the time, but so sort of funny I didn't do it here, but I got it working now. Yeah.
Yeah, great. I'm just going to fetch some water, okay? Just 1 minute. I'm back.
So to
let's
show
see.
the information from Mondays, would I use a slice?
So let's see. So Monday, of course, you need to know that it is on this column, day of week, and it is numeric. So you need, to know that one corresponds to Monday. And so, but basically you need a filter because, you only want to show the rows for which the day of the week is 1, which are the Mondays, okay? So from all the rows, you just want these rows with this property. The slice will not do it because you don't know. The slice works by saying, well, I want this row with this number. But for that, you would need to look at all the data and see which rows, what is the number of the rows for which the day of the week is 1, which would be, bit. And so that's what actually filter does, but it does that for you. And so for the number 4, for each combination of month and day of the week, obtain the maximum and the minimum temperature of the sand location. So basically, I created a group by month and day of the week, and then summarize by calculating the mean of temp sand and the max of temp sand. Okay, again with the NA removed because otherwise I'll get lots of NAs. So as you may have seen, the slide handouts on the web page do not contain the solutions. Otherwise, it will be not be very funny, this part. But I would post the solutions over the weekend on the website. Okay, so I'll post slides with the solutions, so you don't need to copy this if you don't want.
I find with my data sets, often I'm subsetting data a lot and then working with the subsets. But
Yeah.
can I do this instead of subsetting?
What do you mean? Do what?
Well, I guess, it's grouping.
Yeah.
I guess what I could do is like, maybe you could just filter down. Is that the same as subsetting?
Well, filter is, getting you a subset of your rows that satisfy some condition, okay?
Mm-hmm. Yeah.
While group by, it doesn't, group by just groups
Everything.
rows according to the values of one variable.
Mm-hmm.
And so there will be as many groups as there are values on that variable. So it's slightly different, you see what I mean? So some situations what you want is to create, to apply group by. In others, what you want is really filter, because filter allows you to say, well, I want only these rows that have these conditions, which typically are comparisons between the variable and some value. Let's say day is 1 or temperature is greater than something. So you cannot do these comparisons with the group by. Okay, but you can do that with the filter.
Okay.
All right, so it's time to move forward, otherwise we'll be even more late than we are already. So let's move into the next one, which is on data visualization. Oops. All right, so I did already some mess here because my computer is so slow that okay. So now we are going to move into data visualization, and we are going again to base our what's happening? I'm sorry, but I'm having serious difficulties with it. So we are going to again focus on one particular package that I think is the best for data visualization in R. As soon as my computer wakes up. I don't know if this is general or this is just my computer, but anytime I'm doing a web conference over Teams, this is just so slow. So now it decided to open on a different screen. Okay. Okay, so all right, finally, I guess. All right, sorry about the delay. So as I mentioned, now we are going to talk about data visualization, all right? Okay, so motivations for data visualization. Well, we all know that we as humans are really very good at detecting patterns and structures with our eyes, and so data visualization somehow tries to capitalize on these abilities and to try to convey information through by means of graphical plots, or in this case statistical plots, because we are talking about data. Okay. Nevertheless, in spite of all of these advantages, they also have limitations, because typically visualization tools work on bidimensional infrastructures like the screens or a paper, and whenever we have data sets with a large number of dimensions, sooner or later we have to face this reality that is not easy to look at the data visually when it is so multidimensional on these screens or paper because of these two dimensions limitations. Okay, but anyway, it is indeed a very nice tool for exploring the data set, and it is something that I always recommend people to do whenever they receive some data set, to spend some time trying to visualize the data, to try to understand a bit more the properties of this data. Okay, Now, this is a brief outline of what we are going to learn. Some of this, actually, I'm just going to skip because we will not have time, but nevertheless, the slides contain information about these topics, and so later on you can export them by your own, okay? Now, our graphics use a kind of layered architecture. So in one side there is us, our users, and on the other extreme we have the graphic devices, which can be the screen, but it can also be PDF file, JPEG file, whatever. So that's what R calls the graphics devices, which in a way are the devices where the graph is supposed to be output. Okay. And so we as users don't bother about that. We just say, well, I want this nice histogram on the screen, or I want this nice scatter plot on a PDF. And all the work needs to be done by other packages that, somehow make the magic that transforms our instructions, our commands into some output in one of these devices. Okay. Now, we are going to play with one of these high-level packages, which is ggplot2, but there are, standard graphics in R have, other facilities, which is through this graphics package that already comes installed with R, while ggplot2 you need to install before you try what we are going to learn here. Okay. Now, our standard graphics are, okay, they are good. And they include several functions that provide several statistical plots like scatter plots, box plots, pie charts, you name it, lots of them. Okay, so these plots typically are obtained by calling one of these functions. For instance, if I call this in the prompt, I get a scatter plot. Okay, so these functions produce the plot, the complete plot. Okay. Several of these plots can be somehow augmented by adding several elements, for instance, some legend, some text, some line, some arrow, whatever. But these functions produce the complete plot, which you can then augment by using other functions. Okay. Now, as I mentioned, graphic devices are important concepts on data visualization. And our graphics functions produce output that depends on the active graphics device. Okay, the default active device is the screen. Okay, so anytime, so when you run this, it will be output on the default device, which is the screen. Okay, so the default device is the screen. But there are several other graphical devices in R, like the PDF device, the JPEG device, and so on and so forth. And if you want your plot to be output in one of these devices, which basically in this case, these examples here on the slide are files. A PDF device is a file, a JPEG device is a file, a JPEG file. So the only thing that you need to know is, well, how to tell R, well, from now on, my output is not to be shown on the screen, but on the PDF device. And you give the file name. Okay, so that's the only thing that we need to do. The rest, the code to generate the graphics, the plots, doesn't change. It stays the same. Okay, so I have here some example. So for instance, if I do this on R, on my screen, there will be a scatter plot. But if I do the same exact thing, but before I say JPEG and I give a file name, this instruction here tells R, well, from now on, the output device is this JPEG file. And when R sees this plot, it knows it needs to convert this scatter plot to JPEG, and it does that for you. Okay, and so the output will be sent to this file, and then you can close the device. And once you close the device, you go back to the screen. Okay, if instead you prefer a PDF, then you could say something like that. Okay, most of these functions then have some parameters that allow you to control the aspect of the plot on the file, but you see the idea. Okay, so by default screen, but with these functions you can direct or redirect the output to other devices, like for instance JPEG, GIF, PDF files, and so on and so forth. Okay. Now, let's now move into this package named ggplot2. So this, as I mentioned, is an extra package that you need to install. Okay. Now, this package implements the ideas of this book, the Grammar Graphics, the package implements this book is a book about the theory of data visualization, and it actually proposes a grammar to describe any statistical plot. Okay. And so ggplot builds upon this theory by implementing this concept of layered grammar graphics. Okay, so this grammar defines a statistical plot as a kind of mapping from your data into properties, for instance, the x-coordinate, the color, the y-coordinate of objects that you have on the plot, like a point, a bar, a line, and so on and so forth. So you'll get the idea soon. Okay, but that's the idea. We essentially define this mapping, and I'll give you some concrete examples. So according to this grammar graphics, so the key elements on a statistical plot are the data. Of course, without data we have nothing to show. Then aesthetic mappings that I'm going to tell you what it is. Geometric objects, which are the things that are shown on the plot. Statistical transformations, scales, coordinate systems, and faceting. So according to this grammar, these are the basic concepts that allow you to describe any statistical plot. Now, let's see what we mean by each of these entities. So aesthetic mappings are the way we control the relationship between the variables in our data table and some graphic properties. For instance, eventually I could want to map the temperature variable on my data set. Suppose that I have a column named temperature. I could wish to, map the values of temperature into the x coordinates in a scatter plot. By this I mean, well, the values of temperature will be mapped into the x coordinate of some object, which in this case will be a point, because a scatter plot consists of a set of points. Or for instance, I could map the species of a plant into the color of some dots in a graphic. Or I could decide to map the citizenship of a person into the shape of a dot, or the age of the car into the line width of lines in a graphic. So all of these are examples of these aesthetic mappings, where we decide that we want to map concrete values of variables in our data into properties of objects in a plot. Okay, so that's the idea of aesthetic mappings. So depending on the objects that I want to show, we will need more or less properties. For instance, a dot needs at least the x and y coordinate. So I need somehow to map some variables into these two properties. Okay. All right. So geometric objects are the things that we show on the plot. Okay. So we could decide to show each of the rows of our data set by a point, for instance. By mapping two of the variables of my row of my data set into the x and y coordinates, and so on and so forth. Anyway, so the geometric objects are the things that we want to use to convey information about the data. Okay, what we want to show to the user. Statistical transformations allow us to calculate and do statistical analysis on the data and then plot the results of this analysis on the graph. Okay, so for instance, I could use the data and do some transformation to approximate it by a regression line. Okay, this regression line is a statistical transformation from the data. Okay, and then I could show this line on my plot. Or for instance, I could count the number of occurrences of certain values of a variable. for instance, the number of females or the number of males, and then show this count, which again is a statistical transformation because the counts are not in the data, they result from the data, and show these counts, for instance, as eighths of bars. Okay, so statistical transformations do this. Scales, decide how the values in the data are mapped into their static properties. How a value of, let's say, 29 on temperature is mapped into a value of X coordinate. Okay, so the scale defines this mapping. Coordinate systems, typically we use the Cartesian coordinate system, but of course you can also use other coordinate systems which are not so frequent, but that's possible also, like the polar coordinate system. And finally, faceting is another important concept because it allows you to split the data into subgroups. So this is similar to the concept of group by that we have just seen on dplyr, but in ggplot is called faceting, but it allows you to create subgroup or split the data into subgroups and then draw a different plot for each subgroup. Conceptually, they are the same, the plots, but they are being applied to different subgroups of your data to allow you to contrast these subgroups. And we are going to see an example of that. So let's see a concrete example. So let's first look at the plot. Okay, so what you see here is a scatter plot, right? So yeah, you see here lots of dots. Actually, some of them are dots, others are triangles, and others are squares. But basically, you see points in this X and Y coordinate. And you see here that the X coordinate of these points is somehow a reflection of petal length, and this Y coordinate is a reflection of sepal length. Okay, so what you are seeing here is the 150 plants of the iris data set being represented according to their petal length and sepal length, and then each of the plants having a different shape and color depending on the species. And you have here a legend to tell you that. Okay, so how do we translate this that you see here to this concept that I just described? And actually, how do you produce that in ggplot? So you, of course, need the data. That's what I'm doing here. You need the package. And I'm also loading another Excel package that has lots of color scales. And I like this color scale because it's for supposed to be good for colorblind people. And so that's one of the many scales that you have available here. But that's an extra that you actually don't need because the plot would be shown equally, but with different colors. Okay, but anyway, let's move into what is really important, which is how I construct this plot. So the first thing I do is I call this function ggplot, and typically here I say, well, what is my data? Okay, and I'm saying, well, my data is this data frame iris. Okay, and now I have a set of layers which are added on top of this. So this is an extraction that can be written on the same line. So on top of this base layer that simply states that this is the data I want to show, I'm adding a geometric object which is a point. Okay, and a point needs to have X and Y coordinates, and that's why I'm saying, well, to draw your points, use this mapping. X is mapped to petal length, and Y is mapped to sepal length. Moreover, the color of the point is mapped to species, and the shape of the point also mapped to species. Okay, and so this would be enough to generate this plot. The rest is just to make the ggplot use these nice colors which are good for colorblind people. Okay, but that's an extra that you could avoid. Okay, so what we are doing here, well, first of all, we are saying what is my data source. So this is a kind of template. So what is my data source? Then what is the object that I want to show in the plot, which in this case are points. So all these functions start with geom underscore something, geom histogram, geom bar plot, and so on and so forth. Okay, and then depending on the object, I will have different mappings because different objects have different properties. Okay, and I declare these mappings using this AIS, which comes from aesthetic mappings function. Okay, and then I may have eventually other layers. Okay, now both these data and mapping components can be either defined locally by geometric object or globally by for all the geometric objects, because actually on the same plot I could have more than one geometric object, and if they all share the same mapping, I could put it here. I would put data iris, comma, mapping, and the aesthetic mappings shared by all objects, or they can be done locally like I did here. Okay. Now let's move into concrete plots. Okay, and let's start with techniques to visualize amounts. Okay. So let's, visualizing amounts allow us to compare the magnitude of a set of numbers. And this eventually we may have interest to do these comparisons across different groups or subgroups of our data. And we'll see examples of that. So one of the tools for comparing amounts are bar plots. Okay. And bar plots essentially display this set of values that we want to show as heights of bars. Okay, so let's work with an example data set. Let's suppose that we have a table with data about the wins and losses of NBA teams on different seasons. And here I'm just showing you the first rows on different seasons for the Atlantic Division. Okay, and so our data has these 4 variables: team, wins, losses, and season. And then we have different values of these variables. Okay, let's play with this data set. So bar plots have 2 frequent settings. Either the values, the amounts that I want to show are already in the data set, or they need to be calculated or computed from the data. Okay, let's see examples of that. So let's suppose that I want to show the number of wins in one season. Okay, so this number of wins are already on the data. So I don't need to calculate anything because I have here the number of wins for each of the teams on a concrete season. So I don't need to compute anything. So in this case, I want bars that reflect these concrete numbers that are already on the data set. Okay, so that's the first setup. The values to show are already in the data set. Okay, and so for that, I use this geom call. This geom call produces a bar plot where the values to be shown are already in the data. Okay, and more specifically, my data is what? Is filtering. Let's suppose that this NBA is that data set that I mentioned, filtering my data source by season 2018-2019. Okay, because I only want to show the number of wins for this season. Okay, so that's my data. And then the mapping for the columns, for the bars, is that the X coordinate is the team, you see here, the team. And the Y coordinate, which in this case is the height of the column, is the number of wins, which is another variable. Okay, and so that's what I get. Okay, so geom call is used whenever you want to generate a bar plot when the values are in the data set, which is the case of this number of wins. Okay, when you need to calculate the values, you use another object, as we are going to see. It's not the geom call, because the geom call just shows what it is on the data. Okay, by the way, this is a bad design for this plot. Why? Well, first of all, you see here the legend, the names of the teams are too big, and so it's, overtyping on top of each other. So that's a bad job. Okay, so let's try to improve some of the aspects of this which are not so good. So the first thing that I decided to do is to order the bars. Why? Because, yes?
Louis, I don't seem to be able to find the MBA data.
No, you don't have it. I mean, I'm just using as an illustration, okay?
Oh, okay, sorry, okay.
Okay. So in this case, the first thing that I decided to do is, instead of presenting the bars like this, because there is no order among the values of team, okay, I decided to order the name of the teams by decreasing number of wins. And that may seem a detail, but actually helps the reader to understand or read this plot, okay? And so whenever the order of the values has no meaning at all, then it makes sense that you present either in decreasing or ascending order for better readability, okay? And you can do this by, applying the same exact instruction, but here, the X setting mapping, you say that instead of saying X is team, you say X is the reordering of team by decreasing wins. If you want increasing, you omit this minus, okay? And that, changes the order of the bars. But that also still leaves us with the problem of the labels, okay? So what you can do to solve that is to apply to the same statement this coord flip. This coord flip flips the coordinates. X becomes Y and Y becomes X, okay? On the screen, of course, or on the JPEG. And that immediately, shows you in a much more readable way the names of the teams. You could also maintain this vertical aspect and then use some angle here to avoid this overplotting, okay? But that would decrease, and in my opinion, is not so readable as this way, okay? So that's, just minor details which are important to correctly convey information visually, which is your goal after all. Now, let's now see an example when the values that you want to show through a bar plot need to be calculated. Okay, so let's suppose that I want to show how many teams had a percentage of wins larger than 30% per season. So I don't know how many teams have this property, right? It's not on the data. So I need to calculate that. So in that case, when the data, the values are not on the data, I use, instead of geom call, the bar that counts this thing, because what we want to know is how many. So we want to count how many rows satisfy this criteria, okay? And how do I do that? So I filter the data, okay, by this expression. What is this? Wins divided by wins plus losses greater than 0.3. So that's, eliminating any team that doesn't have, more than 30% wins. Okay, so this filter here, which basically it's dplyr, what we learned before, filters from the full data set only the rows corresponding to teams that have more than 30% wins in a season, okay? And now I want to know how many they are, okay, for each season. So for season, let's say 2015, 2016, how many teams satisfy this property? That is not in the data, it needs to be calculated. And that's what geom bar does. So I say, the data is this, and then the mapping is, well, the X is the season, because I want to do this per season. And then I say geom bar. And so this geom bar is going to count how many teams exist per season. But because they were first filtered by this, that corresponds to how many teams have more than 30% wins per season. Okay? So whenever we want to show something by a bar which is not in the data, we use geom bar. If it is in the data, we use geom call. Okay. Please note that in this case it would not be correct to reorder the bars by decreasing order. Why? Because there is a temporal, these labels have meaning and they have an order, a temporal order. So I don't want to swap the order of the seasons because there is a temporal order. So in this case, I would leave the plot as is. Okay. Now, bar plots are nice, but they have several problems. So first of all, the bars must always start from 0. And this creates a visualization problem known as zero baseline. And that happens whenever, the bars have very similar height, then because they all start on 0, then it's very hard to perceive the differences between the bars, okay? And so bar plots should not be used in these situations, and dot plots are preferable, okay? So for instance, instead of showing like this, and this is actually not a good example because the bars are rather different, but just to tell you how to do a dot plot instead of a bar plot for the same information. So if I want to show, the number of wins per team on the season, which was the first plot, we did this, but we could show the same information as a dot plot like this, okay? So in this case, the advantage is not large because the bars are really rather different, but if the bars were very, similar, then this would be much clearer. Why? Because this doesn't need to start on 0, as you see here. Well, this one, the bar plot needs to start on 0. Okay, so dot plots are preferable and they show the same information for this case. Now, sometimes I want to use bar plots, but to contrast groups. Okay, so contrast these amounts for different subgroups. So for instance, let's suppose I want to know the number of wins of the teams along the seasons. Okay, so I could do this with this statement. Okay, so I use the geom call because the number of wins is in the data. And so then I could, map X to team, and it's X because I'm using this coord flip. So without this, the graph will be, flipped. Y is the number of wins, and then fill of the bars is the season. And because there are different seasons, then automatically R or ggplot deduces that you want 1 bar per season. And of course, it will use different colors to make the readability easier. Okay. And so you can, either have the columns on top of each other, or you can have them side by side, like using this position. Okay. So here you can contrast the number of wins per season with the seasons being represented by different colors. Notice that, all the legend and things like that is done automatically. Of course, you can change this thing, but, it always has sensible defaults. Now, and that's, without the position dodge that puts bars side by side, it will stack them, okay? Which, sometimes is interesting, particularly if you want to compare the totals. But in this case, I don't think we want to compare the totals, and so the more adequate would be this one. Okay, but if you want to compare the total across all the seasons, then these stacked bars are easier to do. Okay. Now, another way is to use facets. So as I mentioned in the beginning, facets allows you to contrast groups. So I could say this, I want a column, a bar plot showing the wins and the team. But then I add this facet wrap season. So that means I want this by subgroups formed by season. And so this because the graph conceptually is the same, is a geom call of team per wins. But this one is obtained only with the data for this season. This one is obtained only with the data for that season, and so on and so forth. So that's what facet wrap does. It allows you to create subgroups of the data according to some property, which in this case I said according to season. Okay, and then I decided to coordinate flip again because of the labels. Okay, so this is nice because automatically you may have noticed that the the coordinates, the ranges are exactly the same, and that is on purpose to allow our eyes to more easily compare across each of these panels. If the ranges were not the same, that comparison would be much harder. But ggplot takes care of that for you. Finally, you could also compare these amounts using a heat map. Okay, so you could again have season and a team, and then have this kind of tiles where the color of the tile corresponds to the number of wins. So lighter color is larger wins, darker color is smaller number of wins. And that is done like this. So the data, X season, Y team, fill, the fill of this object, this tile object as a property which is fill, not only X and Y, it also needs to be filled, and the fill is according to wins. And because wins is a numeric variable, it creates a kind of scale of color automatically for you. If wins was a nominal variable, then it would select specific colors for each of the values, and that is done automatically for you. All right. Okay, so let's move very quickly because we are really running out of time. So I think I'll need to skip some of this part because I would also like to talk about models. But the next thing that I want to talk is about visualizing not amounts, but distributions of values. Okay. Now, the goal of these graphs is to understand how the values of a certain variable are distributed across our data set. Okay. And we are going to distinguish two common setups, a single distribution and multiple distributions. Now, histograms are one of the tools that are used for that, for showing the distribution of values, and they look like bar plots because they are formed by columns, bars, but actually they are built in a rather different way. So the number of bars in an histogram is determined by a sort of binning process that divides the range of a numeric variable into a set of bins, and then for each bin I count how many values fit this bin, and that determines the height of the bar. Okay, so that's the idea of how histograms are obtained. So in ggplot you simply do this. So you say, well, from this data set, put on the x-axis sepal length, and then I want an histogram of this continuous variable. And that automatically splits the range of sepal length according to some bins, and then counts the number of occurrences of each bin, and then you get this. Okay, so the number of bins that you pick change the aspect of your plot. So histogram uses some algorithm to determine that, and it warns you that it is using 30 bins. So it divided the range in 30 bins. That's why you see here 30 bars. But you may think that this is too granular, for instance, and you may wish to change the number of bins. You can do that by adding here, instead of using the default, adding here, well, I just want 10 bins. Okay, and so this is the same variable, the same histogram, but the number of bins here being used is 10, and here is the default according to the default algorithm, which in this case would lead to 30. Okay, so it's always a good idea to try several values, because depending on the domain, you may think that something is a bit too brittle or not. Okay. Now, density plots are an alternative to histograms to show the distribution of a continuous variable. So they basically try to approximate the probability density function of the variable, and they are usually obtained with kernel density estimators, and typically the Gaussian kernel. But that's the idea. They try to approximate, in a way they give you a continuous version of these histograms, okay, by using these kernel density estimators. So you can obtain that by using this geom object, geom density. You see, one continuous variable on the x-axis, and then geom density. Then it has several parameters. That's not necessary. You could just call geom density without anything. Here I just decided to fill the density with orange and with some level of transparency so that you can see the axis. Okay, but that's just a minor visual detail. Okay. Now, box plots are also nice tools to show the distribution of continuous variables. They provide a kind of synthetic representation of the distribution by calculating a few statistics, namely the median, the quartiles, and also whether there are outliers or not. Okay, so for instance, you can obtain that with this geom box plot, and what you see is for a continuous variable, what is the median, which is this bar here, what is the third and the first quartile, which are the values below which there are 25% or above which another 25% of the values, and then these limits here, if you see some dots, it means that the variable contains outliers according to the box plot rule, which is one possibility to determine whether a value is an outlier or not. Okay. Now here I just added a few things just to eliminate here the ticks here on the axis and the legend, because in this case it doesn't make sense. But this again is optional. Now, another thing are empirical cumulative distribution functions that I'm going to skip. I'm just going to tell you what they are basically, but I'm going to skip because we are running out of time, so I'm going to skip. But then you can check these, how they are obtained, and then in case you have doubts, you can contact me. And then also quantile plots that compare the empirical distribution of the values in your sample against a theoretical distribution, for instance, the normal distribution. Okay, and that kind of gives you a visual test of whether your values follow a certain distribution or not. Okay, and they can also be obtained with this. Okay. Now you can also use these concepts to compare multiple distributions. For instance, you could want to have an histogram of, let's say, sepal length, but according to species. And so because there are 3 species on the iris data set, in a way you want to compare 3 different distributions of sepal length for the 3 subsets of values. And this is an hypothesis that I do not recommend, because there is lots of overplotting. So histograms, even if I use this kind of transparency level, they are very bad for this purpose. Okay, so that's something to avoid. Much better is to either use facets, where you generate the histogram, but then you say, well, facet by species, like we did before, and then we have an histogram for each of the species. This is much better. Or then use density plots, which with the appropriate level of transparencies are much better than the histograms. Okay, so that's a possibility. And with box plots, it's even better because then you can have one box plot for each of the species. And you can see here that, for instance, for Virginica, there is one value which is extremely low compared to all the others, and it's considered an outlier. Okay, but you can immediately see that settlers have much smaller sepal length than versicolor and then Virginica. Okay, then there are lots of things that you can add. I'm just going to skip. You can actually put the points, the concrete values here, over plotting on the box plots. You can also have some kind of violin plots that look like a mixture of box plots and density plots, and you can do all sort of fancy things. Have the density and the box plot and the points. You can really mess around with this thing, but I'm going to skip this in the interest of time. Okay. I have also examples with the CDFs, and then I had here an exercise. So now we have a decision that I want to for you, and maybe Danny can have an idea. So I either stop here and give you time for doing this exercise, but that means that I'm not going to be able to speak about the modeling part, or I skip this and I go directly to the modeling. What do you think?
Yeah, I have a sense that you should continue on. Yeah, I think that would be
this
good.
one. Skip this one, you mean?
Yeah, I think so. That we can do this on our own. If we,
and I will leave the solutions as I mentioned. So then you can check whether it is correct or not, and you can contact me, of course. Okay?
Yeah, very good.
All right, so let me see if so for some reason, not being able to exit this. Okay. So let's see. Oh, come on. I'm sorry, but my computer is not opening the right sync. Oops. When you are in a hurry, then things get messy. Ah, come on. Why is this a joke? I'm trying to open the slides, believe me. It's not easy. Let's see if like this ever. I apologize for this. This never happened to me, but I don't know why. My computer is not collaborating as it should.
Sometimes I find with my Macintosh that it stays up all the time. I rarely ever boot it. Sometimes I just find I have to take it down and restart it after a couple of months because it never seems to fail. Yeah,
but it's failing on me now. It's saying that the app is open, but it's not open, so I don't see the app. So
it's slow. My Macintosh will slow down sometimes, but it never seems to kind of die. So I have found on occasion that when I have shut it off and then brought it back up again, it works a lot better.
Yeah, but there is no time for that now.
yeah, true.
I'm going to do a last try, otherwise I'll skip to a different program to show the slides, which will mess my head, but I'm losing too much time on this, sorry. Okay, so I'll give up and no. Oh, okay. So now, when I was giving up, it appeared. So, okay. So let's just move the slides. All right, so let's now try to very, very quickly give you some idea of modeling in R. Again, this is going to be very, very quick. Right, so first of all, of course, we need to understand what is prediction. So prediction essentially is the ability to anticipate something that we don't know, which frequently occurs in the future, okay? So of course, prediction is only possible if we assume that there is some sort of regularity in what we observe. And so that means that essentially what we observe is our data, and we are assuming that the data is not random. So we are assuming that we can find some sort of regularity in our data, and that regularity allows us to make predictions for things that we have not seen yet. Okay, so for instance, in medical diagnosis, if we have, let's say, an historical record containing both the symptoms observed in several patients as well as a diagnosis made by a medical doctor, then we could, using this historical record, we could try to model the relationship between these symptoms and the diagnosis. And, with that model, we could try to make forecasts or predictions for new patients for which we only know the symptoms. Okay, and of course that is only possible if we assume that there is, this is not a random process, which we expect not to be in this case. Okay, now prediction models, of course, are obtained based on the assumption that there is some sort of unknown mechanism that maps the characteristics of this observation. So in that example, the symptoms of a patient into the conclusions or what we want to forecast, which in this case is the diagnosis. Okay, and so the goal of prediction models is to try to discover this mapping, this mechanism. Okay, so going back to this medical diagnosis, what we want to know is how the symptoms somehow influence the diagnosis. Okay, and it's this mapping from symptoms to diagnosis that we want to approximate or to find using some predictive models. Okay, so the idea is that we are given a data set that contains examples of this mapping, that is, examples of patients for which we know both the symptoms but also the diagnosis of made by a medical doctor. Okay, now that we have these examples, this data set, we try to uncover the relationship that maps, the symptoms into the diagnosis. So the descriptors of the observation into the prediction. Okay, so that's the game that we are playing here with predictive analytics. Based on this data set with examples of this mapping, this unknown mapping, we want to approximate it using some model. Okay, now the entities involved here are, first of all, the descriptors, which basically are variables that describe interesting properties of the cases. And then there is a special variable that we call the target variable. And that is the variable whose values are supposed to depend on the others. So going back to the example, the descriptors will be the symptoms and the target variable will be the diagnosis. Okay, the diagnostic. Okay, so that's the idea. So the goal is to approximate this function that maps the values of these predictors of these symptoms into the values of one variable, which is this target variable, whose values are supposed to depend on that. Okay, so that's the idea. The goal of the modeling techniques is to approximate this function using the data that we have available. Okay, so we are going to distinguish, two main usages of these models. The first one is the most important or the most common, which is prediction. So once we obtain this approximation, we want to use it to make predictions for new observations of the same phenomena, for new patients, let's say. But also sometimes we are interested in looking at the model and understand the patterns that this technique discovered on the data, which may be novel for us or not. Okay. Now we are going to distinguish two types of prediction problems. What we call classification problems, which are problems where the target variable is nominal. Okay, so it could be the name of a disease, for instance, or it could be the species of the plants on this iris data set. And then regression problems where the target variable is a number. So it could be the price of, let's say, a house, or the price of some stock. So we are going to distinguish between these two types of tasks, regression and classification. Now, also important before we start to talk about models are how are we going to decide whether one model is good or not? And that has to do with how to evaluate the models, okay? And so that has to do with metrics that we are going to use to characterize how good or bad are the predictions made by the models, okay? Now, I'm going to simplify this because there are many more metrics, but I'm going just to talk about some of the most common. So for classification tasks, that is when the target variable is nominal, error rate is one of the most frequent metrics. Error rate basically counts the proportion of errors on the predictions of the model. So if I say this model has an error rate of 30%, it means that on the predictions that I asked the model to make, it made 30% of errors, okay? The complement of this is sometimes also used, which is the classification accuracy. Okay, so that's the formula. Basically, we compare the prediction of the model with the truth, and then we count the amount of errors and we calculate the proportion. Okay, now sometimes we also like to describe the performance of a model, of classification model, in a confusion matrix. So let's suppose that this is the iris data set where the outcome is one of the three possible species, Setosa, Virginica, and Versicolor. So what we could do, suppose that we have, an extra sample of, let's say, 500 plants, we can ask our model, what do you think this plant is? Is it a Setosa, a Virginica, or a Versicolor? And then we count the amount of times that it was observed that the plant was a Setosa, but the model predicted Setosa, or the model made a mistake and predicted Versicolor, or the model predicted, a Virginica. So these numbers here reflect the performance of the model. So if we have only numbers different from 0 on the diagonal, it means that it was accurate always. And of course, that's the ideal. But if we have numbers which are different from 0 outside of the diagonal, then we have some mistakes, some errors. Okay, and so of course the error rate can calculate from these numbers. Okay, now if you want in R, so suppose that you have here the true values, let's say, of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 test cases. And let's suppose that some model, wherever the model is, made these predictions for these 10 cases. I could, with this table function, obtain a confusion matrix that tells me, well, there were 2 times on the 10 that the true value was C1 and the model predicted C1. So this was, 2 correct predictions. But there were 3 times where it was C2 and it predicted C1, and so on and so forth. Okay, so that's a confusion matrix calculated from these, random values that I just put here, just to tell you how to obtain a confusion matrix in R. Okay, and then from this matrix you could very easily calculate the error rate by summing, the diagonal of this matrix, dividing by the total, and then 1 minus that is the error rate. Without the 1 minus is the accuracy, which is the sum of the diagonal divided by the total. Okay, so that's for classification. For regression, we because in regression we have numbers, what we do typically is that we calculate the average of the squared error between the prediction and the true value. Okay, so we do something like this. We have the prediction of the model for one test case. We subtract it by the true value, we square it, and then we calculate the mean of these for a set of test cases, and we have the mean squared error. Okay, so that's a possibility. Sometimes people prefer to calculate the root mean squared error, which is the square root of this, because it comes on the original units of the variable, because this is squared. Okay. Now, sometimes people instead use the mean absolute error, which is, instead of squaring, you calculate the absolute deviation. And, that's another possibility. And other times people prefer relative error metrics, which are unitless, okay? And so an example is, the normalized mean squared error, where you compare the squared error of your model against the baseline. And frequently this is, always predicting the average value of the target variable. So your model is supposed to have less error than this very naive model that always predicts the average. So you are supposed to get a score which is lower than 1. If that is not the case, then it means that your model is even worse than predicting always the average, which is not, very good. You can also do the same thing with the average, the absolute errors. You can also calculate the mean average percentage error, which is a bad idea if the target variable can reach 0, because then you have divisions by 0, and you can kind of avoid that by using these other metrics that I put here. Okay. Finally, people sometimes like to calculate the correlation between the predictions and the true values as a measure of how good the predictions are. Okay. Now I have here our code similar to that one, where I have 10 values and 10 predictions, and then formulas to calculate all these metrics in R. I'm going to skip this because I'm actually running over time. All right, so the first model I had here to talk about with you was one of the simplest and most used model, which is linear regression, which is probably the most used statistical method. And essentially it tries, I'm going to skip this very quickly, it tries to fit to your data a function which takes this shape. So it's a kind of linear combination, which is the equation of an hyperplane on these p dimensions, okay? And so it assumes that the model follows, the target variable is related with the predictors in this way, okay? And then it basically tries to estimate these parameters, okay? And that, there are lots of, matrix operations that make this very efficient to obtain, but that's the idea of this very common model that I'm sure you all are familiar, okay? So this is a very, well-known and overstudied topic. There are books and lots of books about this, so I'm going to skip this. But it has, the basic advantage that it is very interpretable. It's easier to interpret the model, and it is computationally very efficient. Okay. Now, what I wanted, given that we are already at 9 o'clock, to tell you is to give you an example of how to obtain these models in R. So I decided to change this the standard way that I teach that, because I wanted you to be aware of a new package, which is this tidy models, that is becoming, a trend in the R community, and I indeed believe that this is going to be the way that all models are going to be obtained in the future. So there are other ways. There is a specific function in R for obtaining linear regression models, but this thing is more general, and it can be, it has several advantages that I do not have time to talk about now. But believe me that these tidy models will be, the norm sooner or later in terms of modeling in R. But essentially, what you do is that you kind of specify the model that you want to obtain. And in this case, I'm saying, well, I want to obtain a linear regression. But then, because in R there are several different implementations of this concept, linear regression, I have to say, well, and I want to use this particular function that implements linear regression. But there are other possibilities. And what this does is that it sort of generalizes the concept of linear regression, and then it allows you to use different implementations of this concept, okay? And you have the same thing for other modeling techniques. For instance, decision trees are another family of models. Support vector machines are another family of models, but all of them have different implementations in R. And so what you do here is that you add a kind of specification. I want this type of model, and for now, I want to use this implementation of this model. But later on, I can change this, and the rest of the code stays the same. So once again, like in dplyr, the idea is to generalize the concepts and make your code more robust to slight changes. So in dplyr, if I change the source of the data, the rest stays the same. Here, I can change the engine that implements linear regression, and everything else stays the same. So that's the more or less the motivation for this. And then once I have the specification, I can apply this specification to a concrete data. And in this case, I'm using a data set that comes from this package, okay? But that's the idea. So I'm saying, well, use this specification and apply it, fit it to this data, okay? And this is actually where the modeling takes place. This is just an abstract specification of what I want, okay? And so that's the idea. And then, of course, you have here the outcome of the model. And because we have to stop, I understand that, I'm going to very briefly show you what would happen, for instance, if instead of a linear regression, I would like another model. I would simply change the specification, and then this part, the fitting, would be the same, but I would use a different model for this, okay? And so that would be a way of going if I wanted to try other model. So once you have the model, then you can apply it to new data. And then here I'm showing you some other functions of these study models that allow you, for instance, to split your data set randomly according to some proportion. In this case, I'm using 70% split. Then I can fetch the proportion used for training, and then a proportion that will be the remaining 30% that will be used for testing. Okay? Then I can use the same model specification and fit the model only to the training data, which is 70%. Then once I have the model, I can use the function predict to apply this model to a new data set, which will be the remaining 30% that I split here originally. Okay? And then there is another function that calculates lots of the metrics. There are more, but by default it calculates the root mean squared error, the R-square, and the mean absolute error that we have spoken before. Okay, and so all of this, is being developed because this is kind of still very novel, but there are already, a huge amount of models available on this framework, and there is a book that I can point it to you. A free book about this that I really strongly recommend that you read in case you want to get serious about modeling in R, okay? And then, of course, you can do things like plotting and so on and so forth, okay? Now, I really apologize for this because I knew that this was going to happen, but now I would have, other models, but of course, we have already run over the time and I don't have time to show you the slides, but you have the slides, and in case you have doubts, please do not hesitate to contact me and send me an email, and I can try to explain them in case that things are not clear. Okay, sorry about this, but we are running out of time. Okay, Danny, yeah.
Yes, thank you, Louis. Just looking at, you have a tab in your the workshop information called bibliography. Is the book you're referring to amongst that?
Let me see. If not, it is here. It's this URL.
It's called Tiny Model. Yeah, it is. Max Kuhn and Julius Silver.
Yeah.
It's there, and that's
there?
free on. It's there it is. Yeah, okay, I found it. Okay, that's good.
Yeah, I was not sure, but I thought yeah.
It's there. Yeah.
Yeah, it is here. Yeah, so this will point you into this thing. Okay, so this is actually all of this this tidely modeling and also this dplyr and ggplot. All of this is being developed together by a team of scientists in RStudio. So all of this is part of the same. You can see the same sort of philosophy and the same use of dplyr and ggplot and the chaining operator. All of this is being developed together. So I think it will be the norm very quickly in R.
Right. Well, thank you ever so much. I think we should just
new for me also, and actually, this is the first time I'm showing this material to anyone. I'll change my classes for the next semester here in DAL, but my students have not seen this yet. But so this is relatively new. So you are the first ones to see these slides.
Well, that's good. Maybe we should just open it up as if there's any general questions from anyone that's still with us here. There's
sorry about
it's a long session, and for those that hung in there, thank you very much. Any particular questions, Louis?
Too late for that, I guess.
I just had one thought and I just lost it. What was it? I know what it was. It was, of course, deep learning is something that we're all hearing about, and we're using it quite a bit, particularly around imagery and that sort of thing. One of the questions I know I've had, and I didn't know the answer, was how easily does R play with some of these deep learning libraries like PyTorch?
Well, so I have here. Let me see if I see. So I have the list of models that currently are implemented on this framework. And you see here, where is MLP? You see here Keras, which is a Python library for this sort of things.
Okay.
So this is being also integrated within this framework. Okay. So, but it is, I mean, from R, independently of this package, from R, it is possible to connect to most of the Python libraries for deep learning.
Okay, interesting. Very
But
good.
it's being integrated here also. So you have here already Keras. Okay.
All right. Oh, very good. So unless there's no other questions, again, Louis, thank you very much for taking the time to put this together and to present it. And I know first time around, it's always tricky, and particularly we had some problems there with the chat, but I think we'll have to try to work through that. It seems like MS Teams always throws us a wrinkle every time we do one of these things.
Yeah, my software also played tricks to me, so no worries.
Yeah. Okay. Well, thank you so much. I guess we'll close it down. Kalani's going to be sending around a kind of a survey to everybody, just a post survey to get some feedback, and we'll share that with you.
Okay. And, thank you very much.
Oh, thank you. No, appreciate it.
All
and
right.
Thanks everyone that hung in there, and we'll keep you informed of anything else that comes up in terms of workshops or presentations from the Institute of Analytics.
Okay, I just wanted, to again apologize for this rush, because I'm sure that I would need at least the double of the time. But if you indeed have any questions, do not hesitate to contact me. Okay.
Great, appreciate that.
Bye-bye.
Yeah.
It was a great session. Thank you.
Yes, very good.
Bye-bye.
Thank you very much.
Love the session.
Thank you.
Okay, good night, everyone.